Section 13.5, Gravitational Potential Energy. All right, so we're moving beyond force to now talk about potential energy. Note that gravitational potential energy is a property of a pair of particles. You can't divide up to say like, okay, the apple has this much potential energy and the earth has this much. It's not that part of it belongs to one or the other. There's always a pair there. And this is a little bit different than how we've treated it previously, right? We've often talked about the gravitational potential energy of a baseball, but that's within the ball-earth system. So that's why we're able to focus on just the ball itself and not the earth. And the reason we can get away with that is because most of the energy change, almost all of it, is in how the ball moves, right? That as the ball loses potential energy, it gains kinetic energy, and the earth stays about the same. So this only works for systems where one object's way smaller than the other, way less massive. If you have two massive objects, like two planets, now we need to consider how they both have this pair of potential energy, and both of them are really critical. It's just we often zoom in onto the near Earth surface zone where it's just assumed that's all relative to Earth. But the grander scale, we do have to consider both. So the full definition of our gravitational potential energy is a bit more involved than just mgh. For a two-particle system, we would write it as negative g, that's our gravitational constant again, times m, one of the masses involved, times little m, the other mass involved, divided by r. So that's how we can calculate it. It looks a lot like our force equation with a few couple differences here, right? The r is not squared. This is r to the first power, or -1 power since it's in the denominator. And note that it's negative. What does this mean? Well, because it's negative, the potential energy, as you get closer and closer, as the objects get closer and closer together, the potential energy gets smaller and smaller. It becomes more and more negative. As they get further and further apart, as r approaches infinity, because r is in the denominator, the magnitude gets smaller, but it's becoming less negative. It's approaching zero. So moving them further and further apart, you're actually increasing the potential energy. So the gravitational potential energy of a system is the sum of the potential energies for all pairs of particles. So for instance, we have three different particles here, m1, m2, m3. If we want to describe the potential energy of all three of them, we have to consider the potential energy of first particles 1 and 2, then the potential energy of particles 2 and 3, as well as the potential energy of particles 1 and 3. And so each of those terms would appear, and we would just sum up those potential energies to describe the net potential energy that is present. Now, I mentioned before that this potential energy is really similar to the force. We can actually derive that force equation, Newton's law of gravitation, by taking the derivative, right? If we remember from chapter 8, a lot of this is going back to chapter 8, the force is related to the potential energy, and that's negative the derivative of the potential energy. So if you start with your potential energy, U is equal to gmm over r, and you take the negative derivative with respect to r, that's our changing variable, you'll find that the force comes out to positive g m1, m2 over r squared, where the m1 corresponds to big M, m2 corresponds to little m. The only thing really changing here is that we went from -1 over r to +1 over r squared. And you can show that. I'm happy to check your work on that, or it's in the textbook as well if you'd like to see a bit more details on that. All right. Now, also going back to chapter 8, we saw previously that the gravitational force is conservative. Remember, if a force is conservative, that means the work done does not depend on the path followed by the particles. Only the difference between the initial position and the final position, wherever that is. We just care about those two endpoints. So since the work done is independent of path, the gravitational potential energy change is also independent of path. So we saw this equation actually back in chapter 8 for conservative forces that have a potential energy associated with them. The change in potential energy is just negative of the work done. and it just depends on those endpoints. So U final minus U initial. An example of this is shown here, where we have Earth and say a spaceship flying through the air. It starts at point A, then goes B, C, D, E, F, G. Cool, it's following this great path, but we don't actually care about the path that it follows. All we care about is where it starts and where it finishes, and how the potential energy would change, which is just going to depend on how far away from the Earth it is. So it could go in a straight line to G, or it could take some crazy path to G. Either way, the work done will be the same. And it'll be the same change in potential energy as well. Now, if we imagine something trying to leave Earth, we could actually calculate how fast it needs to be going from the surface of the Earth in order to make a break for it, in order for our spaceship to make it out of the atmosphere, for instance. So for a projectile, something that we're launching, like a rocket, to escape the gravitational pull of a body, it must come to rest only at infinity, if at all. And remember, infinity isn't literally infinitely far away, it's just far enough away that there isn't a significant gravitational pull. So at rest at infinity, that means our kinetic energy, once we're infinitely far away, is 0. And that's a point where our potential energy will also be equal to 0, because as r goes to infinity, potential energy approaches 0. So that tells us that K plus U, the mechanical energy, must be equal to 0 at the surface of the body. So if we look at the initial kinetic plus potential energy, which are when a rocket is on Earth's surface, we have the countdown timer going, it's getting ready to launch. When it launches, it needs to have this kinetic energy of 1/2 mv squared, and it will have a fixed potential energy of Gmm divided by r, where r is the radius of the Earth, because it is on Earth's surface, it's at the full radius. And this kinetic plus potential energy at the initial case will have to be equal to the kinetic and potential energy, the mechanical energy, at the end, which at the end, the kinetic and potential energy are both 0 once it's infinitely far away. So if we know that the mechanical energy is equal to 0, then we can start with the initial ones and solve for V. So add the Gmm over r to the other side, divide by 2, divide by little m, the little m will disappear. We take the square root, and that gives us V is equal to the square root of 2 Gm over r. This is known as the escape speed, or the escape velocity. It's how fast you need to be going to leave the Earth, or to leave some other planet. So an interesting tidbit here, rockets actually launch eastward to take advantage of Earth's rotational speed in order to reach this speed more easily. So they use Earth's rotation to give the rocket a little bit of a boost, because once it has this minimum speed, they'll be able to leave Earth's gravitational pull. So I mentioned that you could calculate it for the Earth, and that's done here. We have the mass of the Earth. This is a nice reference if you ever need to look it up for a problem. Mass of the Earth, radius of the Earth, and so the escape speed is 11.2 kilometers per second. That is super fast. That needs to be able to travel at that speed. Notice the moon is much smaller, about 100 times smaller in mass, and the radius is a little bit smaller, but only maybe 5 times smaller, less than 5 times smaller. So because the mass is so much smaller, the escape speed is significantly less on the moon. You don't need to use nearly as much rocket fuel to leave the moon as you do to leave the Earth. Right, Jupiter, oh, that's really hard to leave because Jupiter is so massive. Escape speed is nearly 60 kilometers per second. And then you could go to the sun. The sun's 10 times faster than Jupiter. And then we could get into things like a neutron star, which is so dense, so massive, with a tiny, tiny radius, right? Notice it has about the same mass as Sirius B, but the radius is so tiny that the escape speed is very, very high. And that's why black holes, they say you can't escape, because it's so much mass in such a small radius that it becomes nearly impossible or impossible to actually escape. It's too high of an escape speed even for light to escape, which is pretty wild to think about. All right, so we've seen these ideas. Let's now look at a checkpoint. You move a ball of mass m away from a sphere of mass m. 1. Does the gravitational potential energy of the ball in the sphere increase or decrease? 2. Is positive work or negative work done by the gravitational force between the ball and the sphere? So I want you to think about this, so please go ahead and hit pause now. Okay, I'm trusting you did that. So let's think about this for a moment. This one gets a little weird. I'm going to suggest we actually start by thinking about question 2, which is a little bit counterintuitive. Usually they set up to go from 1 to 2, but 2 I think is a little easier to conceptualize. It's asking if you're doing positive or negative work as you're moving the balls away from each other. Well, to figure this out, we first want to think about what's the direction of the force between these two balls. Well, the gravitational force we know is attractive. So they feel a force that they're getting pulled towards each other, right? They feel this inward force. But we're now moving them, or moving one of them away from the other. So it feels this force towards it, but it's getting moved in the opposite direction. For work, we know that it's force dotted with displacement. So if you're moving in the same direction as the force, that's positive work. But if you're moving the opposite direction of the force, that's negative work. So this is a case where I'd say it is negative work, because we're moving, the displacement is in the opposite direction to the force. With that in mind, we could go back to the first question of gravitational potential energy, if that increases or decreases. Well, we know the change in potential energy is negative of the work. So if the work done is negative, the negative of a negative is a positive. That's an increase in gravitational potential energy. But this feels a little weird. Why is it weird? Well, because these are negative numbers. Our gravitational potential energy is negative, so that feels weird to try and figure this out. But you can conceptualize it that, hey, if I'm moving further from the surface of Earth, my gravitational potential energy is increasing. You could also try it out with some numbers, right? Just to get a sense of it, of how it's changing, right? So I could say, I have some initial, I'm going to stop sharing for a moment just to highlight this. So some initial potential energy is negative g m all over, say, 1 meter. Okay, and then I move my ball further away, so move it to, say, 2 meters. I don't know the other numbers, but I'm just focusing on that one. So g, negative g m all over 2. Just simplify that down. All right, my gravitational potential energy change, if it's increasing or decreasing, will always be final minus initial. And so here my final is negative g m all over 2 minus my initial, which it knows it's minus a minus. That's the key here, of g m all over 1. So that minus a minus becomes plus. And I get GMM minus half GMM. And so that just comes to positive half GMM. And the key here is really just that sign. The 1/2 is just arbitrary based on those random distances I chose, but because it is positive, that tells us that it is an increase. Now we can double check our answer real quick. So we go on, and indeed it does. Potential energy has increased, and it is negative work that is done. The opposite is true of the potential energy and the work. They have the opposite sign. If you don't feel good about that, you can keep wrestling with it. Maybe you have another explanation that makes sense to you. I would love to hear it. So please let me know if you have something that helped it make sense to you, or if you're still confused. We can talk more. All right, we will wrap it up there.